Okay, today we're going to look at rational expressions, which are fractions in which the numerator and denominator are both polynomials. So let's start by considering a numerical fraction with a numerator of 3 plus 5 and a denominator of 3 plus 7. If you look in example 1a, that same student that usually makes errors, did a simplification and it's incorrect. If we think about simplifying fractions, what's wrong with that? The student did not cancel factors. If we think about what the numerator is actually 8, the denominator is actually 10. 3 is not a common factor to 8 and 10. So the student actually canceled what we call terms instead of factors. Factors divide evenly into the numerator and the denominator. So keep that in mind. If we want to correctly simplify the fraction in part B, we need to add to get 8 and 10, and then we need to factor a 2 from each the numerator and the denominator. Then we can grab our handy-dandy red cancellation pen and cancel the 2's to get a final result of 4/5. Okay, so the same thing is true about simplifying rational expressions. If I want to simplify a rational expression, I'm going to write the numerator and the denominator in factored form first, and then I'm going to cancel the factors that are common to both. Notice the word factor. That's a very, very important term with regard to what we're doing today. All right, so in example 1, if we want to simplify each expression, we can factor the numerator and factor the denominator. 6 factors into 3 times 2, and 2x plus 6 has a common factor of 2, so we can factor that out, and there's an x plus 3 left in the denominator. Now you'll notice that the numerator and the denominator both share common factors of 2, so we can cancel those. And the final simplified result is 3 over x plus 3. What I want you to notice is we are not going to cancel the 3's because the 3 on the bottom is not a factor, it's a term. In other words, it's not multiplying, but it's being added. In B, we can factor the numerator. There's a common factor of m. And then we can also factor the denominator. M squared is written in expanded form, m times m. Cancel those common factors of m, and then the fraction that's left is m minus 5 over m. Again, notice that we're not going to cancel the factors of m, or we're not going to cancel the m's, because m is a factor of the denominator, but it's not a factor of the numerator because there's a minus sign that follows it. All right, in C, we can factor the numerator. There's a common factor of 5. So that is 5 times c minus 3. And in the denominator, there's a common factor of 3. So that is 3 times c minus 3. This time, you'll notice that the c minus 3 factors cancel, and what we're left with is just a numerical fraction, 5 over 3. Okay, getting a little bit more involved in D, we factor the numerator. We have a common factor of 5y, and that leaves us with y minus 3. And then downstairs in the denominator, we have a common factor of 10y squared. And then that leaves us with a remaining factor of y plus 6. Okay, if we want to factor further, we can rewrite the 10y squared as 2 times 5 times y, and then cancel the common factors of 5 and y. That's going to leave us with a final result of y minus 3 in the numerator and 2y times the quantity y plus 6 in the denominator. In E, we have a common factor of 5 in the numerator, so that's 5 times a plus 7. And you'll notice that the denominator is the difference of two squares. So if we factor the difference of two squares, that factors into a plus 7 times a minus 7. Time to grab the handy-dandy red cancellation pen and cancel those common factors of a plus 7, and the result is 5 over a minus 7. In F, you'll notice that we have trinomials. Now, we may have talked a little bit about this trick for factoring trinomials quickly if the leading coefficient or the x squared coefficient is 1. That's true in the case of both the numerator and the denominator in example 1F. So we're going to use that shortcut. I'll go a little bit slowly for this. If you're factoring x squared plus 4x minus 5, it's going to factor into two binomials. Since the leading term is x squared, the first term in each binomial has to be x. That's the only way that we can get a product of x squared. Now, the ending terms have to have a product of -5 to get our last term. The thing about this that relates to the AC method is that those factors of -5 have to add up to +4. So they will be +5 and -1. You can check that by multiplying, and we'll get a product of x squared plus 4x minus 5. This is going to save us a lot of time when we deal with rational expressions in this unit. You will want to get very quick at your factoring. If you're going to do the AC method, which you still can, you need to do that off to the side. I don't want to see your factoring in the middle of a fraction. Okay, in the denominator, we have a similar setup. We have x squared plus 2x minus 3. A, the first coefficient, is 1. So that means that the first term in each of the binomials, each of the binomial factors, that is x. The last terms have to have a product of -3, and they have to add up to +2. So those will be +3 and -1. Now you'll notice that both the numerator and denominator contain a common factor of x minus 1, and we can cancel that, leaving us with a final result of x plus 5 over x plus 3. Don't be tempted again to cancel the x's. Those x's are terms. We can recognize that because they're separated by from the 5 and the 3 with a plus sign, not times. Times separates factors. All right, in G, one of the things that you might notice about this one is that the numerator is not in descending powers. The first thing that we're going to do is to write the numerator in descending powers and the denominator in descending powers. And then you might also notice that the numerator has a leading coefficient, the coefficient of m squared, that is negative. That means we're going to factor out a negative GCF. So if we factor out -m, that leaves us with m minus 6. In the denominator, m squared minus 36 factors into m plus 6 times m minus 6. Now we can grab our handy-dandy red cancellation pen, and the result is -m over m plus 6. In H, we'll have to do something similar as well. The numerator is in descending powers of A, so I'm going to leave that one alone. The denominator is not in descending powers of A, so I'll rewrite it in descending powers. The numerator can factor. We have a common factor of A, and that will leave us with A minus B. Downstairs, we can factor first out a GCF of -1. If the leading term has a negative coefficient, we want to factor out -1 first. You'll notice that we can factor the denominator even farther. A squared minus B squared factors into A plus B times A minus B. Now we can cancel some common factors. By the way, a comment about canceling. Generally speaking, we don't want to completely scratch out our work because remember that the teacher still needs to read it even though you've canceled common factors. Okay, so our result is -A over A plus B. Remember that the negative sign can travel from the numerator to the denominator, and we still have the same thing. For example, 3 over -5 can also be written as -3 over +5. We could just let that negative sign travel. It looks a little bit simpler to have it in the numerator rather than the denominator in example 1H. Okay, in example 1I, we're going to put the numerator in descending powers first, -3x plus 6, and downstairs, x squared minus x minus 2 in descending powers. The numerator has a GCF of -3 since the leading term is negative. We'll want to factor out a negative GCF. And in the denominator, you'll notice that we have a trinomial with a leading coefficient of 1. That means that the two binomial factors must each start with a term of x. Secondly, the factors of -2 that add up to -1 are -2 and +1. Now we can cancel the x minus 2 factors, and the final result is -3 over x plus 1. All right, on the next page, we want to simplify this expression, and this one looks a little bit more beastly. It's very tempting to cancel the m plus 3 and the m plus 5 factors between the numerator and the denominator. However, you'll notice that the numerator is not in factored form. What clues me in about that? The minus sign that sits in between the m times m plus 3 and the 4 times m plus 5. So what I'm going to need to do is I'm going to need to, like we did in the very first example, I'm going to need to multiply out what's in the numerator Since the denominator already has 3 factors that are multiplied together, I'm just going to leave it factored. Okay, so in the numerator we have m squared combining like terms minus m minus 20. And downstairs we have those 3 factors that were in the original problem. Now let's skip to the next line. The numerator can be factored using our shortcut that we now have for factoring a trinomial with a leading coefficient of 1. The 2 binomial factors need to start with m, and we're looking for factors of -20 that add up to -1. Those are -5 and +4. Now we can look at what may cancel between the numerator and the denominator. And the factors of m plus 4 cancel. That leaves us with m minus 5 over m plus 3 times m plus 5. And that is our final simplified form for that fraction. In example 3, we need to look at division and a little bit about division because this will help us understand rational expressions a little better. And we think we've talked about this before. 6 divided by 2 is 3. Why is that? Because 3 times 2 is equal to 6. 20 divided by 5 is 4. Why is that? Because 4 times 5 is equal to 20. 7 divided by 1/2 is 14. Why is that? Because 14 times 1/2 is equal to 7. Now I want you to notice something about the check on each one of these. We're taking the result and multiplying by the denominator or the divisor, and we should end up with a numerator if our division is checking correctly. Okay, so now let's look at 0 divided by 7. That result is 0. Why? Because 0 is the number that when you multiply it by 7 gives you back the numerator of 0. Same relationship is true for that division. 3 divided by 0 is, think about this for a minute, it's actually undefined because no number times 0 is 3. Similarly, if we try to do 0 divided by 0, that's also undefined. Now, it's not because I can't think of a number that times 0 gives me 0. It's because it doesn't matter which number I pick. So that one's not defined. It doesn't give me a specific numerical value because all numbers times 0 give a product of 0. So what does this mean? Summarizing, if only the numerator of a fraction is 0, then the fraction is 0. If the denominator is 0, the fraction's undefined. So we can use that to analyze some of these rational expressions. X plus 3 over x minus 4. Let's take a look at what happens if x is negative 3. If x is negative 3, then we can replace the x's with negative 3. And we'll get a result of 0 over negative 7. And we know that when the numerator of a fraction is equal to 0, the fraction's value is 0. In example 4b, x is 4, so I'm going to replace the x's with 4. And we get 7 over 0, which is undefined because we know that when the denominator of a fraction is equal to 0, the fraction is undefined. In C, let's plug in the number 5 for x. The numerator gives us 10 minus 10. The denominator gives us 25 minus 25. This is 0 over 0, which we know is undefined because even though the numerator is 0, the denominator is also 0, which makes the fraction undefined. So if we want to know for what values of x each of these expressions is undefined, we can find where our denominator is equal to 0. So in example 5a, 3x minus 6 is equal to 0, and that gives us a value of x equals 2. So x equals 2 makes that fraction undefined. In example 5b, the denominator is equal to 0. So that means that x plus 3 is equal to 0, and that x is equal to negative 3. X equals negative 3 makes that fraction undefined. In C, if we set our denominator equal to 0 to find where the fraction is undefined, x squared minus 7x is equal to 0. This has more than one solution, and we can find that by factoring. And so both of those values will make the denominator equal to 0 and the fraction undefined. In example 5D, we can again set our denominator equal to 0 to find where the fraction is undefined. And then solve by factoring. And this is one of our shortcut factorings. And we're looking for factors of negative 2 that add up to negative 1. Those are minus 2 and plus 1. So either x minus 2 is equal to 0 or x plus 1 is equal to 0. So there are two values, again, that make this fraction undefined. They're positive 2 and negative 1. One last thing that we're going to do is to complete a table of values for this equation and then plot its graph. So let's plug in some x values, and I'm just going to pick negative 3, negative 2, negative 1, 0, 1, 2, and 3. And let's plug them in and see what happens. 3 times negative 3 minus 3 over negative 3 minus 1 gives us negative 9 minus 3 over negative 3 minus 1. It's negative 12 over negative 4, or positive 3. We plug in negative 2. We get 3 times negative 2 minus 3 over negative 2 minus 1. It's going to give us negative 6 minus 3 over negative 3, or negative 9 over negative 3, which is positive 3. Now we can do this for a lot more values. Let's just do a sample a few more. If we use 0, 3 times 0 minus 3 over 0 minus 1 is negative 3 over negative 1, which is positive 3. I'm getting the impression that our y values will always be 3. Now there's going to be one exception, and that is the number 1. So let's plug that one in. 3 times 1 minus 3 over 1 minus 1 is 3 minus 3 over 1 minus 1, or 0 over 0, and that one is undefined. If we get an undefined result, that's going to result in a place where the graph does not have a y value. So what I've observed here is that to graph this equation, that the y values will always be 3. Let's plot a few points. Negative 3 comma 3, negative 2 comma 3, negative, let's see, we also plotted 0 comma 3. We observed that when x is 1, there's no y value, so I'm going to put a little hole in the graph there. And then I'm just going to extend what we did to realize that the y values are always 3 except for when x is equal to 1. Think about why x equals 1 gives us that undefined value, and that's because its denominator is equal to 0. So If I wanted to simplify that rational expression, 3x minus 3 over x minus 1, I could simplify it by factoring. And you'll notice that the result is 3. But it's not always 3. It's 3 except it's undefined when x is equal to 1. All right, lastly, to graph any rational expression that simplifies, I can do this a little quicker than using a table of values. If I just note any values for which the expression is undefined, simplify the rational expression, and then graph the simplified function, marking the point on the graph where the function is undefined with an open circle, or more informally, a hole in the graph. All right, so let's take this expression right here. Y equals x squared minus 4 over x minus 2. The first thing that we're going to do is to note where the expression is undefined. It's undefined when x minus 2 is equal to 0, or its denominator is equal to 0, or x equals 2. So I can rewrite x squared minus 4 as x plus 2 times x minus 2. Cancel common factors, and then rewrite as x plus 2. Well, we know how to graph y equals x plus 2. That is a line with slope equal to 1 and a y-intercept equal to 2. So that's very easy for us to plot. It has a y-intercept of 2 and a slope of 1. That's going to be in fraction form, 1 over 1, which means that we go up 1 over 1, up 1 over 1, up 1 over 1, or down 1 and left 1, down 1 and left 1 to complete our graph. The last thing that I do before I need to connect this is I need to note where that hole is. There's going to be a hole in the graph at x equals 2. So I'm going to erase that point that I graphed when x is equal to 2, and I'm going to replace it with a hole. Now I can connect the graph, just noting that there's a hole at x equals 2. In B, we can first note that the fraction is undefined when x plus 1 is equal to 0, which means that x is equal to negative 1. So remember, we're going to have a hole in the graph at that point. Now let's simplify the fraction. Factor the numerator. It factors into x minus 2 times x plus 1. Cancel common factors. And then our graph is going to look like just plain old y equals x minus 2. That's also a line with a slope of 1, or 1 over 1, and a y-intercept of negative 2. So we can graph the y-intercept of negative 2 and a slope of 1. This time you'll notice that our hole is at x equals negative 1. So I'm going to put a hole in the graph at the point where x would equal negative 1 and connect. And that's it for today's lesson.